Hi, everyone. I hope you've been enjoying the session so far this morning. Just a reminder that after all of the sessions at the end of the day that we are heading over to Poor Girl right over here on College for some drinks and food. And after the next session, it will be lunch, and there are lots of places right along on College to grab a bite to eat. Our next presenter is Taz Singh. He is a software architect, CTO, and organizer of JavaScript and Toronto Code Retreat groups. He's here this morning to talk about the different JavaScript virtual machines and their approaches to concurrency, garbage collection, just-in-time compilation, and optimization. Please welcome Taz Singh.
Perfect. Thank you so much, Carolyn. So as Carolyn introduced myself, I'm Taz Singh, and I'm here to talk about JavaScript virtual machines. So while doing research on this topic, I found a lot of other talks on JavaScript virtual machines had some sort of car involved. They all had some sort of like race car or racetrack or engine or something like that. So here I'm sort of obliged to have some sort of picture of a car. So here's my picture of a car. It's sort of off the screen. It's just that big. Can we do anything about that, Matthew? Okay, I'll have to fix that then, because we won't be able to see a bunch of the slides. That's my balcony. Woo! All right, sorry guys, give me 1 sec here. Of course. What is it, 1024, 768?
Yeah, do that one.
Okay, cool.
And then don't forget to start the other.
Oh, whoops, confirm, all right. Sorry.
The other software. Quit, start. There you go.
Okay, let's get going. So there's my car picture that I'm obliged to put up because I'm giving a talk on virtual machines, and in this case, the car is a Radical SR3 race car. There's a lot of downforce on that car, very large engine, so you can't really see from the picture, but there's a front splitter, rear diffuser, rear wing. There's actually a flat underbody. It's shaped like a wedge. There's a lot going on with this car to make it fast in terms of downforce. There's slick tires in this car, so once these tires warm up, it sticks better to the road. And it weighs about the same as a Harley, but has more than twice the power at very high revs. So you have to understand this car in order to drive it fast. Right? If you take this car into a corner too slow, you're going to spin out because you don't have enough downforce. If you take this corner, if you take a corner and you don't have any heat in the tires, you're going to spin out because you don't have you can't stick to the road. So in a lot of ways, our JavaScript virtual machines are very much like this car, right? You can get pretty damn fast in them, but if you don't know how to use it properly, you're going to continue spinning out. Sure, the machine's going to be fast even though you spin out, but you can get a whole lot faster if you don't. So you're probably thinking, why should I even care about performance, right? I mean, I'm using X JavaScript framework, and that takes care of performance for me. I have some website, and all I'm doing is AJAX calls. AJAX is the thing that takes on, that goes on and on and on, not really my JavaScript application. Why should I really care about JavaScript? Well, let me tell you why you should care. So obviously, JavaScript is everywhere these days. It's used in the client. It's used in browsers, obviously. It's used in native applications such as mobile apps. It's used in it's actually used in Windows 8 apps. You can actually build Windows 8 apps in HTML5 and JavaScript. It's used on the server side in Node.js and Phantom.js, and it's also used in other server-side implementations. But the requirements for a client-side virtual machine are different than that of a server-side virtual machine. So on the client, you don't really know what platform your code is going to be executing on. So it can be executing on 1 core, it can be executing on 4 cores, it can be executing on 1 gig of RAM, it can be executing on 8 gigs of RAM. It's sort of unpredictable. So you care about performance because you can't really predict what client your code is going to be executing on. Server side is a bit more predictable. You know what servers your code is running on. You know what environment they're running on. You know what instruction sets are available. But the difference between a client-side virtual machine and a server-side virtual machine is that server-side has to stick around for a lot longer. Right? In terms of uptime, it has to stay around for days, weeks, months, potentially. Right? So the characteristics of a server-side virtual machine, they have different requirements than that in the client. So compiled to JS languages, obviously performance is important there when you're writing your own or you're looking at existing compiled to JS languages, knowing how they actually perform and making sure that they're performant in all scenarios. And Finally, databases. So these days, a lot of databases have stored procedures in JavaScript, MapReduce jobs in JavaScript, even graph traversals in JavaScript. So MongoDB, CouchDB, React, Orient, and Postgres. And on the topic of MongoDB, since Mongo has JavaScript, and Couch has JavaScript, and React has JavaScript, and Orient has JavaScript, and Postgres has JavaScript, it makes it just that much easier for you to migrate away from Mongo to any one of those other solutions. All right, so which JavaScript virtual machines will I be talking about today? SpiderMonkey. So SpiderMonkey was the first JavaScript engine, famously created by Brendan Eich in 10 days. These days it's used in Firefox, CouchDB, React, and in a few other places as well. I'll be talking about V8. So V8 was created by Chrome. It was released with the first version of Chrome in 2008. It's used in Chrome, Opera, Node.js, MongoDB, Postgres, and elsewhere. Chakra. So Chakra is actually Microsoft's virtual machine. It was introduced in IE9 and is used in every version of IE since then. It's also used in Windows 8 native apps and Windows Phone 7 Plus. JavaScript Core. So this is also known as the Nitro engine. It's developed by Apple, used in Safari, also used in PhantomJS, and in a few other places as well. And lastly, Nasorn. So Nasorn is a new JavaScript virtual machine built on top of the JVM. I won't really be focusing on this one too much, but it's of particular interest to me because I use a lot of JVM-based languages such as JRuby, Clojure, Scala, etc. So it fits into my toolchain quite nicely. So I'll be talking about it a bit later. But anyway, it's still under development by Oracle. It'll be released next year with Java 8, and it uses a bunch of cool things in Java 8, such as native closures, such as invoke dynamic support, etc. But as I said, I'll be focusing on mainly the first four, and then if you have some time at the end, I'll throw in Nasorn as well. Cool, so what are the properties of a virtual machine? Virtual machines are made up of a parser, an interpreter, a garbage collector, and a code compiler. So to go over the parser and interpreter, this is essentially what it looks like. You have your JavaScript code. It gets parsed by a parser, which tokenizes your JavaScript, figures out what you're trying to do, converts everything into an abstract syntax tree. That gets converted to bytecode. So that's what a virtual machine understands is bytecode. It takes that bytecode and then puts that bytecode through an interpreter, which will then generate machine code. I found this interesting about a parser in that if you have something in your code called new model, so NEW model, right? In order for the parser to know that's your code and not the keyword new, it has to go and look at the N in new model and say, oh, you know what, N is used for my code and it's used for the new keyword. You know what, I need to go look at another character. I need to look at the E. Okay, so we have NE. That's still used in the new keyword. Is this a new keyword or is this my code? Take a look at the W. Once again, it's shared between both of them. So it has to take a look at the fourth character, in this case, the capital M or a white space in the case of new, to figure out what it is. So obviously this takes time. And when you have something like instance of or instance of model, it has to look through like what, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 character comparisons before it figures out what's going on there. So I found it interesting that you can actually optimize your JavaScript by just using variable names to start with those letters. So I found that a bit funny. And now I'm not by any means suggesting that you do this. I think that's quite nuts. And don't walk in on Monday and say, hey guys, we're going to just use these letters in our JavaScript. But if you're writing a code minifier, let's say, and you want to like really optimize it, you can use those letters, let's say. But also on that point, code minifiers normally optimize for code size, not necessarily parser execution. So you find that they'll use B's and C's and D's and so on and so forth because they're optimizing for code size. But anyway, that's how a parser works. Bytecode. So given this bit of code here, we have A equals 1, B equals 2, A equals B plus 1, return A. Right? So we don't really need the A equals 1. Right? So as humans, it's very easy for us to just take a look at that code and say, oh, we don't need A equals 1, let's just skip that over, don't worry about it. But for a computer, it has to do quite a bit more analysis on that. It has to do what's called reaching definition analysis, which is a compiler optimization, but it's expensive to figure out that you don't even need A equals 1. So what a lot of JavaScript virtual machines do is they use a technique called single static assignment. And what that does is it assigns to versions of a variable. So in this case, this is just pseudo bytecode, by the way. No actual bytecode in a JavaScript virtual machine looks like this. I just try to make it a bit easier to understand. So this is pseudo bytecode that represents single static assignment. So we can see that the first version of A has 1 assigned to it. The first version of B has 2 assigned to it. The second version of A, once again, we don't overwrite existing versions, we just keep adding versions. The second version of A has the first version of B plus 1, and then we're finally returning the second version of A. Right? So now looking at this, a compiler can easily look at this and and very easily eliminate dead code, very easily remove statements that you don't require. It's incredibly simple. Like you see that the only thing that you're returning is A2. What does A2 depend on? It depends on B1 plus 1. B1 is 2. That's it. We don't even use A1 at all. Virtual machines implement single static analysis to figure out what's needed and what's not. So that's a very trivial case. So let's take a look at this case. A equals 1, B equals 2. We're looping over 100 times, adding A plus B to the value of X, and then finally returning X. So as humans, we can see that A plus B isn't really needed in this loop. We can easily just move that out of the loop and get the same sort of, get the exact same result. But a computer doesn't really know that. So here's the single statically assigned version of that. I'll let you take that in. So we have the first versions of everything defined. We have our loop. And we have T1 inside that loop, which is the value of A1 plus B1, X2, I2, a test, jumping back to the loop, and then finally returning X2. Now, the astute in the audience will probably notice that, we're just adding the same variables together over and over again in this loop, right? We're just adding, X2 is always equal to X1 plus T1. This is an infinite loop right here, right? We're never actually incrementing anything. We're always adding to the same versions. So single static assignment introduces this fee instruction. So what this fee instruction does is it basically says which one of these 2 variables was defined last, right? So in the first iteration of our loop, I3 is equal to phi I1 or I2. I1 was defined last because it's our first iteration. On the second iteration of our loop, I2 will be defined last, right? So I3 will be the same as I2. So this is how it does, analysis to see what's actually needed within the loop and what's not needed within the loop. And once it goes through this analysis, it can easily determine that T1 isn't needed in the loop and just hoist it outside of the loop. This is called code hoisting, or if you want the long fancy name, sounds smart to your code workers, it's loop invariant code motion. That's a mouthful right there. So anyway, just to show you what that does again, you see the T1 is inside the loop. You just move the T1 outside the loop, called code hoisting. Now, JavaScript virtual machines do this for quite a few different things. It does this for variables that are easily computed. In this case, it does this for functions. It does this for variables. Wherever a virtual machine deems appropriate, it can easily hoist code out and do the computation ahead of time and just use that stored variable elsewhere. Lastly, I want to talk about the interpreter. So the interpreter executes machine code based on incoming bytecode. So it'll take a look at those bytecode instructions from before, and based on the platform you're on, it will execute the appropriate assembly instructions. So if you're on x86, it'll generate x86 machine code. ARM, it'll generate ARM byte machine code, etc., based on the bytecode. This means lots of type checking, right? Because you don't really know, especially JavaScript, such a dynamic language, you don't really know what the types are. So the interpreter has to end up doing a lot of type checking. This creates garbage. We don't do manual memory management in JavaScript. We do automatic memory management. So we need a garbage collector in order to collect this garbage. And this creates a lot of garbage for that garbage collector to collect, which obviously takes up time. This is slow, but it works, right? And to give you an example of how dynamic JavaScript is and why virtual machines still have interpreters is because cases like this, right? Array prototype 1 is YOLO, right? We're going to print an empty array of 5 different elements, and the second one is YOLO, right? That's just JavaScript. So in order to make sure this case works, a lot of virtual machines have implemented interpreters to do a lot of type checking, to do the prototype chain lookup, to figure out that the second element is YOLO, and there we go, print it out in the result, right? So we just heard a lot about ASM.js and how ASM.js, you give it a lot of type information so that it can optimize it based on that. This is another example of where we don't have that type information, and we can't really optimize well, so we have to go through an interpreter. And up until 2008, just about everyone was using this technique, bytecode, interpreter, so on and so forth, but then Chrome came out. Chrome came out with V8, and the code compiler was introduced to JavaScript. So this is really where the JavaScript VM wars began. Once this came out, Mozilla came out with TraceMonkey, which was their first JIT compiler, just-in-time compilation tool. And that significantly boosted the performance of JavaScript quite a bit. So on the note of V8, V8 skips the bytecode step. So before I showed you, it goes from JavaScript to the parser, to bytecode, to the interpreter. V8 goes straight from the parser straight to machine code. It skips bytecode, it skips the interpreter, doesn't even have an interpreter. Which, that's a complete game changer to the JavaScript virtual machine space. Interpreted VMs, on the other hand, so everyone else, they use just-in-time compilation. So they will identify which code is hot and then compile that code down to machine code, and then from then on execute that compiled machine code. And it's funny that the interpreted VM guys, they argue that they can start executing code faster than V8 because they don't have to go through the expense of code compilation. They can just stick everything in an interpreter and bam, it's executing immediately, while V8 has to figure out how to compile it to machine code and actually end up compiling it to machine code. But then the V8 guys came in and said, oh, but once we do get going, we actually get going a whole lot faster. So, pros and cons to both. This diagram is actually from the Chakra team at Microsoft. This is how their VM works. So as you can see, the source code gets inputted. It goes through the parser, gets outputted into an abstract syntax tree, into the bytecode generator, generates some bytecode, goes into the interpreter. So the interpreter spins away, doing all your code in it, so on and so forth. So once it identifies hot bytecode, sends it over to the JIT compiler, which is actually unique to the Chakra VM, is that it's executing on a separate core. It's not blocking your JavaScript execution in any way. It's on a separate core. It's completely asynchronous from your JavaScript execution. And once it has compiled that code, it'll then backpatch it back into your bytecode. And as you can see, a little execution block there that's where your code lives. Also unique to the Chakra VM, it uses a concurrent garbage collector, so it's collecting garbage on a separate core once again. So another thing that V8 introduced was something called hidden classes. So previously, in all virtual machines, JavaScript objects were represented as hash tables. So what you have to do is, you have to do a hash key lookup to get a property. And this is fine, this is great. I mean, JavaScript objects are essentially hash tables. You can add properties, you can remove properties. It's very simple, very easy. But the only downside to this is it's slow to look up properties. Right? You have to do you have to use a hashing algorithm in order to look up a property. Things such as pigeonhole theorem come into play. It's a bunch of computer science stuff that I don't really feel like getting into. But anyway, what V8 said was that 90% of your code isn't really that dynamic. 90% of your code is quite static, in fact. Maybe 10% of your code is extremely dynamic. Maybe that 10% works great in hash tables. Maybe that 10%, add, remove properties, whatever. But 90% of your code is quite static, in fact. So it's much faster to do some sort of array offset lookup than doing a hash key lookup, right? So to demonstrate this, I have this bit of code. It's the canonical example for demonstrating hidden classes. So if you've seen this in a presentation before, I apologize. But we have a point constructor, and the little arrow on the left side there shows you where in the code the diagram will be representing. So we have this point constructor. So let's go ahead and start by creating P1. So the little box there, the empty box, is our instance. And that's going to internally point to a hidden class. We just created a hidden class. Next, we're going to assign the X property to it. So this actually creates a whole new hidden class. So we've gone through the overhead of creating a hidden class in the first place. We're going to go through the overhead of creating another hidden class now. And we're going to assign the X property to the array offset of 0 on our instance. And we see that at the array offset 0 on our instance, we have the value of 3. We have the X value. So let's go ahead and add Y. Y is going to create a new hidden class. And it's going to have the property Y mapped to array offset of 1 in our instance. And we can see that the value 4 resides in our offset of 1. Cool. So we just created 3 hidden classes, assigned a few numbers into their slots into our instances. Let's do the whole thing all over again. So P2, we have a blank instance now once again. It's going to point to our initial hidden class. We don't have any properties defined on that quite yet. Let's go ahead and define X. It's going to point to our previously generated hidden class, which has X defined on it at index of 0. And as you can see in our instance, we have the value 5 in index 0. And then go ahead and define Y. So Y is now, once again, residing in array slot 1 with a value of 6. As you can see, we did not generate any new hidden classes. We're just reusing what we had. And this is how JavaScript virtual machines handle fast property access, is by using hidden classes in this way. And as I mentioned, V8 started with this, but since then, everyone's doing this now. Like, SpiderMonkey is doing this now, Chakra is doing this now, JavaScript Core is doing this now. They may call it different names. I think JavaScript Core calls it structure IDs, but it's the same thing. So based on this knowledge, what happens if we do that? Right, what happens if we say p2.z equals 8? Well, what happens is that we create a new hidden class. Who would have guessed? So hidden class 4 now has the z property added to it in array slot 2. And we can see that the value of 8 is in that instance at array slot 2. So at this point in our code, we have the same class. We have 2 points, right? But they're internally mapping to 2 different hidden classes because the properties that we added to them are different in both cases. Now, keep this in mind as this comes into play later. This is very common in a lot of JavaScript applications, and just doing something like this, makes them point to the same hidden class. Assigning z in the constructor, let's say to undefined. You could also, put z in the argument list and then do this.z equals z. But anyway, essentially, you want to always define the same properties in the same order. So if for P1, if we define x, y, z, and then P2, z, y, x, those also would point to 2 separate hidden classes. So we always want to make sure that we're assigning the same properties in the same order to all instances of that class. Cool. So let's move on. Inline caching. What inline caching does, as I mentioned before, the interpreter will run through bytecode and generate machine code, which will then execute on your CPU. What inline caching does is it actually inlines that cached machine code to handle an operation within a function. Instead of generating that code and putting it on a CPU, it'll generate that code and inline it directly within the function for that operation. It handles the optimistic case first. So as I mentioned before, JavaScript is incredibly dynamic. You could have things be an integer 1 minute, like in next minute it's a string, right? It can change at runtime quite extensively. So generally what inline caches do is it handles the optimistic case first, handles the case where they're both integers first. And then if they aren't integers, if that assumption fails, it'll bail out. It'll bail out of that optimization into a slower but more general case, which handles potentially more types. Once again, just to demonstrate this, I have our same point class we defined before. In this case, I'm only defining the x property on it, not defining anything else. And we have an add function, which does a plus operation on both of the a plus b's x properties. And it gives us 8. So this is what an inline cache initially looks like. Check if A is an object, check if B is an object. Look up A's hidden class. Check if A's hidden class has the property x, otherwise bail out. Right? It doesn't even know this up front. It has to check this. Look up B's hidden class. Check if A's hidden class is the same as B's hidden class, otherwise bail out. So as I mentioned before in our hidden classes, if those 2 hidden classes are different, this is what's called a polymorphic inline cache. Polymorphic means different types. A big word for different types. If they're the same hidden class, it's a monomorphic inline cache. Monomorphic, same type. So in that case, we can make additional optimizations just because they are the same type, right? So in this case, we don't have to look up if B has an X property. We don't have to look up where that X property is. We already know it's the same type. Okay, cool, moving on. Look up A's X property, look up B's X property, check if they're both integers, add both integers, and if overflow is detected, bail out to double arithmetic, right? So that's the tool chain that an inline cache will go through. It's probably similar to what a modern interpreter will go to for JavaScript as well. So anyway, the next time around, if we have 2 new objects, that's all it has to do. Check if A's hidden class is the same as before. Check if B's hidden class is the same as before. Look up A's X property, look up B's X property, check if they're both integers, add both integers, overflow, moving on. So as we can see, that's only 7 steps, while before it was 11 steps. So that's how the inline cache will help. And sorry, just to be clear, this is just for the plus operation. So this is not the return, this is not the function call, this is nothing else. This is just the plus operation. So inline caches work only on single operations. Now, what happens if we do this? What happens if we pass in a string of 5, right? So it's going to do the same thing. It's going to go through the same inline cache, check if A's hidden class is the same, B's hidden class is the same, look up the X properties, check if they're both integers. They're not. So this means that it's going to bail, right? As I said, it's optimistic in these assumptions. It's going to optimistically think that they're integers. If any of those assumptions fail, it's going to bail. So it's going to bail out to a more general case. It's going to ask, what do we have here, right? We have an integer and we have a string, right? What operation do we need for an integer and a string? It's going to go out and grab that operation and then perform the string concatenation, right? So this is where we have different type arguments coming in, and this also applies to different types of hidden classes coming in. So if you had 2 different types of hidden classes, one we haven't seen before, the inline cache doesn't know what to do, has to look it up, recompile, so on and so forth. So generating a monomorphic single type inline cache is going to be super fast, while generating a polymorphic one that generate multiple types is going to be much slower because to do a lot more checking and go from there. So like the one hidden class issue I mentioned before, it trickles down to your entire JavaScript code execution. So there's one thing you want to focus on and one thing at all you want to take away from this talk, just do that. And that will, you'll see noticeable speed ups across your JavaScript application, no matter what modern virtual machine you're running on, because they all implement hidden classes these days. Cool, so moving on to code type specialization. Your VM, it employs runtime optimizations, opposed to a compiled language which employs compile time optimizations. So runtime optimizations means that your VM will profile code execution for type information and to identify hot pieces of code, so code that's executing all the time. Compile and inline entire functions based on type information and call sites. So as I mentioned before with the inline caching stuff, it does a lot of type checking. Right? If you're getting the same arguments, the entire function, the types are going to be consistent throughout the entire function. You can therefore inline the type information for that entire function call. And then based on the call sites, based on how that function's called, if it's monomorphic or polymorphic, it can then further inline that code directly into into the call site. So in the first example, we're doing integer arithmetic. It can just literally take that entire code block and inline it directly. Polymorphic is a bit trickier, has to do more type checking, and then finally go to a code type specialized function call. And notably on this as well, IE9 only does monomorphic inlining. So on IE9, if you even did polymorphic inlining, it just won't even inline. It'll just go straight back to the interpreter, which is slow, collects garbage, all of that bad stuff. So you want to really stick to monomorphic, once again, for IE9 performance. IE10 Plus does polymorphic and does a whole bunch of other stuff as well. Microsoft's really worked very hard on Chakra, so it's good to see. Anyway, some pitfalls. So where does this all fall over? So first and foremost, when you're doing property access using square bracket notation, you can't really do fast property lookup. That's because it has to do a hash table lookup based on what you're passing in. So this is slow. Doing a delete operation on a previously fast looked up key. What this tells the underlying VM is, hey, like I'm going to be working on this in, so I'm going to treat this more like a hash table. I'm going to create some sparse keys where, previously where we had the array slots 1, 2, and 3, I'm going to get rid of the middle one, right? Or, sorry, in this case, the first one. What that creates is a sparse object, right? So the underlying VM will say, treat this as a hash. Let's convert everything over to a hash. Let's do hash lookups on that, and that obviously slows a lot of things down. Quite a large client-side web framework actually got rid of a delete that they had in their code base, and I think they assigned it back to an undefined or a null, one or the other, instead of deleting that key. And I think they saw like something like 18% code improvement throughout their entire framework. Something ridiculous like that. So just watch where you're doing these types of things. For that same reason, an array that looks like that will also be slow because the underlying virtual machine that says, oh, this is a sparse array. We don't have a continuous array. We have a bunch of keys that just have nothing in them. So let's represent that as a hash map as well. The with statement. Now, I haven't actually read up anything saying that it's a bad performance pitfall, but just generally speaking, you shouldn't be using it, just because you're introducing a new scope, and then you have to look at the outer scope as well. So you're doing a lot of scope checking within your JavaScript in order to check where whatever you're calling, like which scope does it reside in, and that slows things down. Try catch. So I'm sure you've probably heard the common phrase, just wrap it in a try catch. That actually slows things down in JavaScript virtual machines. So what that does is everything inside that try catch block is not optimized. The V8 won't try to optimize it. None of the other virtual machines will try to optimize it. It will just run as de-optimized. It will run in an interpreter if it has an interpreter. It won't try to do code type specialization in V8. It will just run in inline cache mode. It just won't try to further optimize anything. Obviously, this creates a lot of garbage. It's slow. It's all the bad stuff I mentioned earlier. So instead of putting all your code in a try-catch block, create a function, put all your code in there, and just call that function from a try-catch block. Apparently, that's the workaround for this. That means that the underlying VM can optimize that function and then just call that function from the try-catch block. In my opinion, I feel like the virtual machine should just introduce hidden functions and just wrap the try-catch block in a hidden function to optimize that. I mean, it's an easy case to optimize, but hey, I don't work for Google or Apple or Microsoft or Mozilla, so I'm sure it's much more complicated. Something like this, where you're creating an array and you're pushing a bunch of objects to an array. So in this case, we're pushing 2 integers and a float and then a string. V8 and a lot of the other virtual machines, they represent their call stack as 32-bit pointers, 32-bit, everything's 32-bit. So having a double means that we have to, a double is 64-bit. So that means we have to box our double. What that means is we put it inside an object and then we point to that object with a 32-bit pointer. So that means that we can't store doubles inline in our instances. We have to always reference them. However, V8 and some of the other virtual machines have optimizations for this. So going through this example here with the array, we're pushing 1 to the array. It knows that that's an integer. Cool, we can fit that within our 32 bits. 2, cool, it's another integer. We can fit that within our 32 bits. 10.5, that's a double. What do you do there? So V8 will actually, instead of boxing it and making a property lookup, V8 will convert the 1 and the 2 to a double and just inline everything. So now you have 64 bits of 1, 64 bits of 2, 64 bits of 10.5. So then we go ahead and we add a concern face, right? And what does that do? That tells the underlying virtual machine that, hey, this isn't doubles anymore. These aren't numbers anymore. These are strings. So what that will do is, in fact, undo the previous optimization. It will rebox the double, and then we'll add a string to the end, right? So that's very expensive because we just converted our integers to doubles, converted our doubles back to integers, and boxed our double is just a lot of work. So an easy way to get around that is by doing that. Use the literal syntax. This tells the VM all the information up front so that it knows that there's a string, it knows what to box, it knows how to optimize for that case very easily. You'll get more performance that way. So it looks like we have a few more minutes, so I'm going to talk a bit about Nasorn. So as I mentioned, I do a lot of work on the Java virtual machine. I do a lot of JavaScript code on the Java virtual machine. I use a framework called Vertex, which allows me to expose my server-side event bus to my client. It's awesome stuff. I gave a talk on it a little while ago, which we'll be posting online shortly, and you can check that out. But anyway, Nasorn was coming new in Java 8. So it uses new JVM instructions called invoke dynamic, and as you all know, Java is incredibly statically typed. It's really quite a pain to code in Java because it is so statically typed. Invoke dynamic makes it possible for dynamic languages to run better within Java JVM bytecode. I won't get into details, but it gives you the full access of JVM runtime optimizations to your dynamic languages. So all dynamic languages such as JRuby, JavaScript, I think Clojure can actually use this as well, to optimize their code. Java 8 heap, there's actually no permanent generation, so I don't really touch on garbage collectors that much because the garbage collectors are still quite simple in the JavaScript world. But previously, Java used to create a code cache size. Now, with native closures, the code cache is part of your heap. The same thing applies for JavaScript virtual machines, where your code cache is part of your heap. So, sorry, backtracking a bit. Previously, where I mentioned that polymorphic inline caching is bad, since that's part of your heap, it will get garbage collected with your heap, right? So, if you have a lot of initialization code, which creates a bunch of polymorphic inline caches that slows down your application, garbage collector happens, gets rid of all that. Your app stabilizes, creates monomorphic inline caches, and you're good. So, virtual machines have a lot of safety in this case, and Java is now introduced to that world of native closures and permgen, getting rid of the permgen, code cache, garbage collection, etc. Avatar.js is a Node.js implementation on top of Nasorn. So this actually runs Express, Mongoose. It runs a bunch of the other Node.js libraries on top of Nasorn. And in fact, these run faster on Nasorn because of Java's I/O subsystem than they do on Node itself, which is interesting. Even though Nasorn is a bit slower than Node, Express runs faster on Nasorn, which begs me to ask the question of C extensions. So I'm coming from the Ruby world. I do a lot of Ruby, and I do a lot of JRuby. And in that world, we have CRuby and we have JRuby. And in CRuby, there's C extensions, right? You can write an extension, you can hook into it with Ruby, and execute C code from Ruby. Same thing applies with Node.js. You can write a C extension in Node, and you can call that from Node itself. What happens with that in Java? Is this going to be a repetition of what's been seen in the Ruby world, where there's been a port of C extensions, things such as FFI? What's going to happen with that? So that's sort of like. Oh, I guess I can take a few questions. Now, just keep in mind, as I said before, I don't work for Microsoft, Apple, Google, or Mozilla, so I don't actually work on these. I just think that they're cool and interesting, so I may not be able to answer your questions to the full extent. Yep.
Yeah, so, sorry. Basically what you're saying is you want high performance, so basically write your JavaScript app as statically typed and like with predefined variables, and you shouldn't use many of the dynamic features as possible, right?
In order to get the absolute most of your application, yes, that's how JavaScript machines, virtual machines are currently optimized for. They currently optimize for that case, which is why projects such as ASM.js, which is why they get such great performance, because they give you that type of information, they give you that additional information up front, so that the underlying virtual machine can optimize for that and get blazingly fast speeds. Now, as I mentioned before, the V8 team said that 90% of code is built in that way already. 90% of your code is static. It's really only 10% that is not. So generally speaking, you should be fine anyway. Oh, yep. Yeah, so the previous ones are retained. They're basically collected as per any other object. So I guess sort of backtracking a bit, where are we here? We can see that hidden class 4 has a pointer from hidden class 3, has a pointer from hidden class 2, has a pointer from hidden class 1. So they will be retained within your heap as long as there are references to them. Yep. Oh, sorry. Yep. I'm sure the V8 team would love you if you were to have told them that, if you were to give them that information. But unfortunately, you can't really do that with JavaScript. As I said, like one of the biggest gains with ASM.js is the additional information you're giving the compiler, the additional guarantees you're giving the compiler. In this case, no, you don't have that, unfortunately. Oh, yeah. This one? The one with the bailout or the one without the bailout? Yep. Check if A is hidden class. So in this case, A is a point object. So in this case, like A has a, so I guess going back to hidden classes here, A has a X property, and it has a Y property and has a Z property defined on the hidden class. So the hidden class just tells the underlying virtual machine which array slot to look up. And then from that array slot, it uses something called pointer tagging to figure out if it's an int or if it's a string or if it's an object or whatever else. I didn't get into all that within my talk, but it uses pointer tagging to figure out the value. So it's the same, yeah, it's going to look up the same array slot, but then once it looks at the array slot, it's going to determine it's a different value. All right, so I guess that'll be it. Thank you so much, and I'll be around all day if you want to ask me any more questions or anything. Thank you.